Hey guys, this is Mr. Sal. So in 5.1 we looked at multiplying and dividing rational expressions, essentially polynomials and fractions. But now we're going to be looking at adding and subtracting them, which means we're going to need common denominators. So thanks for watching. Don't forget to like, comment, and subscribe. So for the domain of these, and we've kind of gone over this, is for the denominators, we can have denominators of 0, because it makes it, just as an example, if we were to show this with numbers, right, 5 divided by 0, it could be written as a fraction like this, but if we did long division, it's really 5 divided by 0, and how many zeros go into 5? Well, there's really an infinite number of them, which is why we consider it undefined. And that's why we can't have denominators that are 0. Now we have to be careful with this, because even if we had an expression like this one, we can see that the x minus 3's are going to cancel out as a factor of 1. However, from the original expression, we would still say that x cannot be 3, because it would still make the original expression an undefined value. I mean, we can see hopefully there that x also cannot be 2. So that's the first part, and since we are just looking at the domain for these, we're not so concerned about the numerator, because even if the values cancel out like we just barely saw, it's not going to change anything in terms of how the domain is affected. So for 8, I need two factors of 8 that add up to -6. Looks like it's going to be -4 and -2. So that's our denominator from this, right? I got x minus 4 and x minus 2. And we would really write this as an inequality where it cannot equal 0. So that means that if I looked at the first set, x minus 4, this can't equal 0. So x could not equal 4, just using basic solving equation properties there and rules. But also x minus 2 could also not equal 0, which means that x cannot equal 2. So it wants this in interval notation, and it may help to see this on a number line, right? At 2 and 4. So at 4 it's an open circle, but also at 2. And in addition to that, any values between would make that true, but also to the left and right. So how do we show that in interval notation? We just need to be able to exclude the 2 and 4. And we can do that with the parentheses that we use. So for the red line, we can see that this goes all the way to -infinity, but then it stops at 2, which is not included. And we'll unite this starting at 2, which is not included, going all the way to 4, not included. But we're going to reunite this starting at 4, not included, going all the way to infinity, also not included. Any of the values in these ranges would give us a statement, some statement, from that original function that we started with. So this right here is considered our answer. Alright, so what about this one? Once again, I'm not concerned with the numerator. We'll just state the excluded values on this one, by the way, which is nice, so we don't have to worry about the number line or the interval. Well, from this expression, I can see that I can factor out an x, and that leaves us with x squared plus x minus 20, and two factors of -20 that add up to 1. Looks like that would be 5 and -4. So that splits that up into x plus 5 times x minus 4, but we can't forget about the x as well. As long as this does not equal 0, then we're in good shape. So starting with the red x, well, if that were 0, then that would be no good. So x cannot equal 0, first of all. Then we got this second set here, and so x plus 5 cannot equal 0. So x could not equal -5. But also x minus 4, that cannot be 0. So x could not equal +4 as well. So the final answer, x cannot be 0, -5, and 4. That's not in order, but I'm not so concerned about that if I were looking at a test. All right, when adding and subtracting rational expressions, it's important to remember that we can have, or we need, common denominators. Now, it doesn't have to be the lowest common denominator. We just need any common denominator. If we were to look back at the numbers, what this is saying as well is once we do have common denominators, we can make this one large fraction. So, with addition, if this was 5/7 plus 2/7, we could make this one fraction with 5 plus 2/7, which would just give us 7/7, right, or 1. And that wouldn't matter if we changed that to subtraction there either. If this was subtraction, we just have subtraction there, and then this would become 3/7 instead of 7/7. Now this will be important because we'll need to combine like terms as we add and subtract polynomials, and then there may be a requirement of factoring that new expression out to see if anything can be factored out as a factor of 1. All right, so to get us started, this one gave us common denominators. Well, that's very generous of them. So I can rewrite this as one large fraction with x minus 3 being the denominator. And then I've got my 2x minus 5, and this is being added to the 5 minus x. So I'm just looking to combine like terms on this in order to simplify it. And then we can see if anything can be canceled out. So I got 2x's minus that 1x right there, leaves me with just an x. But negative 5 plus 5 is 0. So those cancel out. So I've just got x over x minus 3. And I'm okay writing it like that. Once again, in the most generous fashion, they've given us common denominators of x plus 2. So I can write this as one fraction, where I've got x squared plus 14x minus, and I will want this in parentheses, just so we can see that we're taking away not only the 14x, but also that 4 right there. Or I can look at this as a negative 1 that I'm going to distribute into the parentheses. So I've got x squared plus 14x, and then I've got negative 1 times 14x, which is minus or negative 14x. Negative 1 times 4 is negative 4. And this is all over x plus 2. And once again, I can see that I can cancel out my 14x's right there, which leaves me with x squared minus 4 over x plus 2. And we may feel pretty good about that. However, we got to be careful because that right there is the difference of squares right here. So this is going to factor out into x minus 2 times x plus 2 with our x plus 2 in the denominator. So that's going to cancel out as a factor of 1, and we're simply left with x minus 2 as our final completely simplified answer. So now we see a new expression, but it has no common denominators, and that's good for us, all right? What I'm going to want to do is put these in parentheses individually, just so when I combine them, I'm not confused about what exactly is happening. Now, in red, I've got an x plus 5 for that fraction, and then in purple, I've got x plus 6. So I need common denominators, and just like we would with a regular fraction to scale it up, right, I mean, I could multiply these just by 3, but I have to make it a factor of 1, so it's really 3 over 3. Now, that's just to show us that we could, right? Or in other words, let me restate that. If I were to multiply this by 1, then I'm in good shape, right? Because it doesn't change the value of that fraction. But I can replace 1 as anything divided by itself, and in this case, I'm going to choose x plus 6 over x plus 6 right here. I may have said that backwards, but now I have an x plus 6 factor for this fraction, and then an x plus 5, which means that my other fraction is missing. Again, I'm multiplying by 1, which is just anything divided by itself. And in this case, I choose that to be x plus 5. So we can see, let me rewrite this expression here, that now we're looking at a new expression, but we have common denominators, which now allows me to make this one fraction. And yeah, I could look at this as though I'm distributing the 1 into both sets of parentheses, right? And yeah, I can just go in there and change that x plus 5 into negative x minus 5, because I could have distributed that as a negative 1. And so now simplifying, I've got this 1x minus this 1x, so that cancels out. And I've got 6 minus 5, which is 1. And then we have that same denominator, x plus 6 times x plus 5. And that right there is our answer. All right, here's a very different looking example. We got that x squared, but and we may be tempted to just put in there plus x here and then plus x there, and then we've got common denominators, right? That's definitely not what we should be doing in this case. What we want to do is really split up these or factor them just so we can see exactly what is needed. So by that, what I mean is I'm going to take this x squared and just make it x times x. And then from x squared plus x, I'm going to factor out an x, which leaves me with x plus 1. So I can see in my denominator, for the red one, I've already got an x to match that purple x, but I am missing an x plus 1 here. Now to make that a factor of 1, I need to multiply it in the numerator as well. So I've got two x's multiplied together times an x plus 1, which means the purple is missing multiplied by x right here, but again, I need to multiply it in the numerator as well. And that gives me the common denominator, x squared times x plus 1, and this was addition, of course, right? And I can factor in my 2 there, so I've got 2x plus 2, and then the red x times 1 is just x. So now if I was looking to combine like terms, I've got that 2x in green plus that 1x there, which gives me the 3x's plus the 2, and then I've got my denominator there, x squared times x plus 1. And this appears to be as far as I can simplify this expression, so that's where I'll stop. Finally, we've got this expression here, and I've got that x plus 10, but here with the x squared minus 100, that's a difference of squares right there, so I'm going to split that up into x minus 10 times x plus 10. And we can see now that these two denominators have the x plus 10 in common, and I have a new expression that looks like this. So I need that x plus 10 in common, which is good because they are. But now I also need, just on the left side, that x minus 10. But I need it to be a factor of 1, so I need to multiply it in the numerator as well. Which means that I can distribute that 4 to make that 4x minus 40 plus the x plus 90 in my numerator all over x minus 10 times the x plus 10. Okay, well let's look to combine like terms here. I've got the 4x and the 1x, which is going to give me 5x's. And then I've got negative 40 plus 90, which is positive 50. And this is all over my common denominator. And this is what we have now. Now again, we may feel pretty good about this because, well, this is where we're used to stopping. However, we do need to take a closer look at this expression and just see that that numerator, 5x plus 50, we could certainly factor out of both of those terms a 5. So that leaves me with this expression here. And yeah, now we can see also that the x plus 10 here cancels out that x plus 10 as a factor of 1. So my final answer really is this 5 over x minus 10. All right, same idea as those last few, right? I have this w plus 3, which is good, but I don't have a w minus 6 there. So I need it, so I'm going to multiply it by w minus 6, but to make it a factor of 1, I need that in the numerator as well, and it may help to see that as two binomials, because it's really w minus 6 times that quantity, w minus 1. Well, now I've got that w minus 6 on the right in the denominator, and I'm missing a w plus 3, so I need it there, but again, I need to make it a factor of 1. So I need it in the numerator as well. Alright? So I'm going to rewrite this now as one full fraction, but because we have the common denominators, right? But now that I have this, I want to distribute so that I can have, well, I want to call it a quadratic, but it'll allow us to see if we have any like terms to combine between the two terms there. So now I have w times w minus 1, and I also got negative 6 times w minus 1, and over here I've got w, oh, there's plus between that, w times w plus 3, it's plus, and also 5 times w plus 3. Alright, well, that gives us more stuff to distribute into the parentheses. We've got the w, the 6, negative 6 rather, w, and then the 5 as well. Well, at this point now, all we're doing is looking for like terms to combine, in the numerator specifically. So I've got my w squared and this other w squared. Now for my w's, I got this negative 1w with this negative 6w's, that's negative 7w's, plus 3w's is negative 4w's, plus 5w's would be a positive 1w. You don't really need the 1 there if you don't want it. Whatever. Then I've got my constants. I got a 6 plus 15, which would be a positive 21. Alright, just to be sure, we should probably see if we can factor the numerator, right? So, for that, I'm looking for a 2 times the c value, 21, which is 42. And I need to see if any of the factors for 42 would add up to 1, which is the coefficient of w. I should have kept it. So let's see, I've got 1 and 42 doesn't work. 2 and 21. So what the heck, 3 and 14, still no good. All the way to 7 and 6, I guess. None of those are good, even if we made them negatives, right? So, as it turns out, that right there, that's my answer. We'll simplify this, and to do that, we're going to factor out this first denominator, well, first, okay? And we'll see, well, I'm sorry, we'll see if it can be factored anyways. There's nothing else that I'm looking at that could be factored, right? Nothing to no greatest common factor from 17 minus 4 or t plus 10. So to do this, I'm just going to factor out 50. I'm sorry, I'm going to find two factors of 50 that add up to 15. 5 and 10 should work. So that now becomes x plus 5 and x plus 10. And the rest of it, you know, stays the same here. Okay. So I have one denominator in red there, that's t plus 5 times t plus 10. And over here on the right, I've just got the t plus 10, which means I'm missing the t plus 5. So again, I need to make it a factor of 1, so I'm going to multiply it in the numerator and denominator. And that gives me my common denominator. Again, this next step that I'm showing isn't one that everyone even feels the need to show. I mean, if you do, hopefully it helps you out, though, okay? So I'm just making one giant fraction now. So once again, it's just one giant fraction there. All right, now what I'm going to do is distribute this negative 3 into this set of parentheses. And yes, it is a negative 3. So that would be negative 3 times t, which is negative 3t. And negative 3 times 5 is negative 15. The rest of it stays. And now we're just looking to combine like terms once again. And I have like terms with my t's. I've got 7 t's minus 3 t's, which would give me 4 t's. And I've got negative 4 and negative 15, which is negative 19. Of course, the denominator is still untouched. I'm looking at 4t minus 19, and I don't see that I could factor anything out of that. If I wanted to force it, I mean, I perhaps could, but I don't see anything that would make it very convenient. So I'm just going to stick with that as my answer right there.